you very much for introduction, and I would like to say thank you all for this opportunity to talk about our work. I will be talking about memristors, and I'll tell in detail what these are, because maybe not all are very well accustomed with this kind of devices. And I will discuss how we can use memristors to simulate brain-inspired neural networks. Yeah, how we can introduce memristors to neural networks. Okay, let's start. So yeah, first of all, this is what I'll be talking about. So first, there will be some quick introduction. What is a memristor? Why do we need it? Then I'll talk about our memristors with which we are working right now, parallel memristors. Then I'll show some results and conclude my talk. So first, why do we actually need the memristors? As you all know, the traditional von Neumann architecture, which is incorporated in all of our computers, have some great advantages and great flaws also. So, for example, the spatial the thing that memory and calculations are in different places, spatially, yeah, it causes the work. It causes our computers to work a little bit more slowly. So basically, if some kind of information is incorporated in the computer, it is stored in the memory, and in order to make some calculations, it should be transferred to the place where the calculations are made, and then transferred back to the memory. So this kind of two-sided transfer from memory to calculations, from calculations to memory, it takes a lot of time and energy. So this is why the neuromorphic networks are of interest, and not only with memristors, of course, but generally of interest, yeah, because memory and calculations are all placed in are all in one place, yeah. Basically, as it has already been said previously, yeah, that this kind of this area is of high interest nowadays. So, and this is understandable, because as long as we have memory and calculations in one space, it simplifies all the process, and it doesn't need extra time to transfer the data from one place to another. So in order to make this kind of neuromorphic network that is presented right here, yeah, it's like neurons, synapses, we need two basic parts. As I have said, yeah, neurons and synapses. Neuromorphic networks have shown that they are very important, for example, for so-called anthropomorphic problems, speech or pattern recognition, and all of these, yeah, images classification, all these kinds of problems. And in order to make a neuromorphic network, not in our computer, but in hardware, in our physical world, we need to have some kind of devices that would represent neurons, and some kind of devices that would represent synapses to construct a neural network in hardware. So neurons have already been implemented in software, in hardware, and a lot of candidates and good candidates for the role of neurons have already been studied. And I guess that it is okay to say that a good neuron nowadays is already made. So neurons are not a problem for neuromorphic network implementation. But on the other hand, synapses are a problem, because there is still no ideal device that would have the possibility to store information, to calculate to make calculations at the same time, spatially in the same place. Yes. For example, a synapse can be created with the help of 6 or 7. I would maybe I am a little bit here incorrect, but I guess about 5, 6, 7 transistors. But and it will have all the characteristics that it should have. But the idea to implement one thing, one synapse with 5, 6, or 7 transistors is not a good idea, because of course transistors take a lot of space, even with further and further miniaturization of these transistors. Still 6 devices for one synapse is too much. As you can see right here, it's a very small neural network, and here there are a lot of connections between neurons, a lot of synapses, and if each synapse is made with 5 or 6 devices, that is too much. So the main idea here is to have some kind of device that would just solely, just alone, have all the characteristics of the synapse that we want. And a memristor is a great candidate for this role. So now I'll be talking about what memristor actually is and why is it so good and why does it have all the characteristics that we need in a synapse. So first of all, let me talk about a memristor, what it is physically. Well, a memristor is a very simple structure. This is actually one of its advantages, that it's such an easy made simple structure. It's a metal, mostly it is a metal insulator, metal sandwich structure. It is presented right here. It's a simplified picture, of course, but basically we have one metal, we put it on the isolator, on the insulator, yeah, and we have another metal contact. So this sandwich structure actually has a lot of interesting characteristics and a lot of interesting and it shows a lot of interesting things that a synapse also does. What does it do? Well, memristors are able to change their conductivity in some window from the high conductivity to the low conductivity under voltage pulses, and store this state for a long time after the removal of the voltage. So basically, if we apply some voltage to the top contact right here, if the voltage is high enough, all of the structure will change its resistive state, which will change its conductivity, yeah, under the voltage. And it won't only change it, yes, it will also stay in this state for a long period of time, even if there is no voltage. So here we can see already some kind of synapse-like characteristics, because the conductivity of a memristor can, we can talk about conductivity of a memristor as the weight of the synapse. So we can change the conductivity as we can change the weight of the synapse. And also the conductivity of a memristor stays the same after the voltage is removed, like the weight of the synapse. So the main idea of these memristor structures are, the main idea is that we have a synaptic-like structure, but the weight of this structure is represented by the conductivity of the structure. And also, it is very understandable. It is just in the name of the structure, memristor. It is the combination of two words, memory and resistor. So it is the resistive memory, if I can say, if I can put it this way. So as I have said, it can the resistivity, the conductivity of the structure can change in some window, yeah, from high to low. And now I'll be talking about the characteristics of these structures. They are very interesting and very exciting because they are very much alike to the synapses ones. For example, here we have a common, very general current voltage characteristics of the memristors. First of all, we have zero voltage applied to it, so the memristor is in its initial state. Then we apply more and more voltage to the top contact of the memristor, and we see that the current through the memristor slowly grows. But here it is still in the high resistance state. So here it is still in its very near to its initial state. But as we come to some kind of threshold voltage, we can see a very quick increase in the current, and it increases dramatically. This means that our memristor is switched to another state, so it is a low resistive state, and it stays in it till 2 volts. And here, this line, it means that we just had some kind of current limit for it not to burn, yeah, for the current not to be very, very high through the structure. So we limited the current with 1 milliampere. And then as we come to smaller voltages, we can see that the state of the memristor changed. So basically, for example, right here, for this voltage, at first it was very low, and here, after it switched, it is visibly higher. But this is not the end, yeah. Even with the negative voltage, the memristor stays in its new state, in its low resistance state, and it switches back only if high enough negative voltage is applied to the structure. Here we can see that we are going here, yeah, and we come back to the high resistance state. So this is a kind of hysteresis curve that is very typical for memristive structures. And we can see that with the applied voltage, we can change the state of the memristor from some high resistance state to some low resistance state. And here it is also once more highlighted that in this way, the resistive state of the memristor represents synaptic weight. What a good memristor should have? Well, as these memristive studies have been conducted for a long time, I think some kind of 50 years or something like that, a lot of structures have already demonstrated this kind of membristic characteristics. If I come back to this picture with the structure of a memristor, a lot of insulators, a lot of metals were studied, and all of them demonstrated membristive characteristics. Well, maybe not all, but a lot demonstrated membristive characteristics, with a lot of this middle layer. A lot of middle layers were studied, and they demonstrated organic, inorganic, with some nanoparticles, nano tubes, and all this kind of stuff. But not all memristors can be held for a synapse. So several memristor characteristics should be I would say should represent synaptic ones in order for memristor to be a good candidate for a synapse implementation. First of all, voltage current characteristics, which I showed before. Yeah, here it is just in a normal scale, and here it is a little bit reversed, so negative voltage. It is shown in but basically, if you want to see this current voltage characteristics as we saw this one, we can imagine that this curve goes right here. Yeah, so we can see that here is also a hysteresis curve, and it switches from the high resistance state to low resistance state, just like before. But we can see here that the memristor has some kind of stochasticity in it. So the red line is the median line, median curve to all of these hysteresis curves. But the gray lines are just how the memristor switched from cycle to cycle. And it can be seen that one cycle it switches one way, another cycle switches a little bit in another way. So this stochasticity, it is an inherent characteristics of the memristor structures. It is a thing that we cannot get rid of, but we can decrease it. The only thing that we can make with this stochasticity is to decrease it. Of course, in order to have a good synapse, we should have low stochasticity in order to create a real structure for a hardware neural network. So this kind of stochasticity is not that good for memristor structure. Also, another memristor characteristics is the number of the stable resistive state of the structure. So as I have said before, yeah, I have shown here two states. It switches from the high resistance state to low resistance state, but also there are a lot of states between these two outmost states. And it can be seen here that I guess that 30 to 64 states can be found for memristor. When I say state, I mean a resistive state, of course, between two outmost resistances. And a memristor with many of the states is considered a better memristor for synapse implementation. So it has higher plasticity as a synapse has. Also, of course, the resistive switching should happen stably. So we should see many stable resistive switching cycles. Here we can see that from the high resistance state to the low resistance state, the structure shows 300 of these cycles. So the structure is first switched to the high resistance state, then to the low resistance state. And this can be continued through 300 of cycles. This is actually not that good of a number. The good endurance would have 1,000 or more than 1,000, 10,000 of cycles. The more, the better. So the more stable resistive switching cycles, the better is the structure. And also, a memristor should be able to change its resistive state according to the bio-inspired algorithms. For example, spiking time-independent plasticity. If it is not able to behave as a synapse, it cannot be characterized as a synapse. So it should be able to change its resistivity in according to the bio-inspired algorithms. In order to I guess all of you know this algorithm quite well, but I'll just tell a few words about it. So we have two synapses, one synapse and two spikes incoming to a synapse, yes. And if a presynaptic spike arrives first and then the postsynaptic spike, then it is a good connection. The effect, causal effect, is held, and this good connection should be strengthened, and its weight should be increased. In this case, not weight, but conductivity. So we can see that if presynaptic spike arrives first and then postsynaptic spike, then the conductivity of the memristor grows, as it can be seen here. But on the other hand, if the first arrives postsynaptic spike and then presynaptic spike, this is not the type of connection that we want to strengthen. We want to decrease this connection. So here we can see that in the other case, the conductivity of a memristor is decreased. So this memristor has lower and lower conductivity, and this weight has lower and lower impact on the potential neural network. So I guess that these kind of curves are very familiar to all of you, and as it can be seen, these kind of curves can be implemented with memristors as well, with good memristors, of course. So here we come to a problem with the memristors, that all of its characteristics should be good in order to create a synapse. So I have told you about stochasticity. Yeah, it should have low stochasticity of all memristive characteristics. It should have high endurance, large number of stable resistive switching cycles. It should have good retention, so it should store its resistive states for a long time. It should have high plasticity, yeah, a large number of stable resistive states. And also it should be able to change its resistive state according to the bio-inspired algorithms. So one structure, one simple structure, sandwich structure, metal, insulator, metal, should have all of these characteristics at the same time. And of course, as long as this field is kind of a new one, there is still no ideal memristor that would implement synapse characteristics ideally. All of the memristors have some kind of flaws. For example, one memristor has a good plasticity, a lot of stable states, but it has low endurance, not so many number of stable resistive switching cycles. There is still no ideal memristor. This is why the study of new memristive structures is a very important field of study, and this is why this field is has more and more works, more and more articles, scientific works in these years. So I'll come to our memristors, to our parylene-based memristors, and I'll tell why we chose these memristors and how we can improve their work, their characteristics. First of all, what is polypara-xylylene parylene memristors? They are organic types of memristors. So this middle layer, the insulator layer, is made from the parylene. This is an organic material. It is relatively flexible, which is very good if we talk about creating synapses for flexible electronics. It is transparent, and it is a very good electrical insulator. So it is a good candidate for this metal layer in which the resistive switching occurs. I will maybe return to this again picture in order to clarify. Yeah, so isolator, this insulator, yeah, layer. Here we have parylene. The metals, they could be any metals. For our work, we chose for the top contact, we chose cuprum, and for the bottom contact, we chose ITO, indium titanium oxide, and it matters a little bit which metal is chosen, but the main resistive switching events, they happen in the middle layer. So this is the layer of the most importance. Okay, so for this layer, we chose parylene. Why actually we want to create organic memristors? Well, their performance, their characteristics are comparable with inorganic ones. The manufacture process of these memristors is very simple. Also, these organic memristors are biologically compatible. They can be flexible, as I have already said, and they could be implemented in a 3D matrix, which is also very interesting in crossbar architecture. We are studying not only parylene memristors. PPX, it's a short name for the parylene, yeah, in order not to write all the time para-xylylene, so we write PPX. We study not only PPX, parylene memristors, but we study parylene memristors with nanoparticles of molybdenum oxide. Why do we do that? Well, we have a hypothesis that we had before a hypothesis that parylene memristors have some flaws that can be improved if we introduce nanoparticles to the parylene layer, and these are the results that I will be talking about. So this was our hypothesis about a year or two ago. What is the problem with the pristine parylene layer? The switching voltages, the voltages which should be applied in order to switch the structure to another state are very high. So this is not good. We want smaller switching voltages in order to incorporate these memristors in the potential future neural networks. And also parylene memristors, they have very high stochasticity. The switching occurs sometimes at one voltage, sometimes at another voltage. This is also not very favorable. This is also very bad. So our hypothesis was that the incorporation of nanoparticles would help us to decrease the switching voltages and decrease the stochasticity. The goal of our work for the last year was to study this kind of nanocomposite memristive structures, to see their characteristics, all of the memristive characteristics which are necessary for the synapse implementation. Also to study the possibility of the resistive state update according to STDP learning rules. Yeah, STDP, spiking timing dependent plasticity. And answer the main question: are this kind of nanocomposite memristors suitable for neuromorphic networks, for neural networks? Will they be okay in hardware, if a hardware neural network is created based on these memristors? So let me switch to the third part of my talk. Basically our results with these memristors. Here we can see current voltage characteristics, hysteresis curves of the pristine parylene memristors and parylene memristors with nanoparticles of molybdenum oxide. It can be seen that pristine parylene switches very stochastically. It can be seen that from cycle to cycle, the switching voltages are different. So at one cycle, it switches at this voltage, another cycle, it switches here. So the stochasticity is very high. And also it can be seen here because the states are very stochastic. If we study statistically the numbers of the voltage of transition from high resistance state to low resistance state and vice versa, we can see that the standard deviations of the mean values are very high. So, for example, it switches at 2 voltages here, yes, this is the mean value, but the standard deviation of this number is extremely high. On the other hand, we can see the current voltage characteristics of nanocomposite parylene memristors right here, and we can see even without statistical numbers that we decreased the stochasticity of resistive switching. Here are presented 100 resistive switching cycles, and it can be seen that they repeat each other quite well. So the switching occurs at the same voltage, the switching from the low to the high, and also vice versa. All appears at the same voltages, and the standard deviation of the switching voltages is very, very low if we compare it to the pristine parylene one. So our hypothesis that the incorporation of nanoparticles would lower the stochasticity was correct. And also, as it can be seen, the voltages decreased, the switching voltages. The mean value here is 1 voltage, and here is 2 voltages. And also for the for the reset voltage, the decrease is also visible. So basically, all of our hypotheses were true for these structures, and so we began studying the structures in order to make a kind of synapses from them. They had high plasticity. It can be seen here that from the high resistive state to the low resistive state, there can be found many stable states. And I say stable is that we do not apply any additional voltage in order to store, in order to maintain these states. So these states are stored without any additional voltage needed. And it is they were stored for 5 minutes without any visible differences from the beginning states, and 32 different resistive states were found for this structure. But of course, here we presented only 5 minutes of the experiment, because it would have been a very long experiment if we had 32 states for a longer time, but we chose 4 states of these 32 states, and showed that not only 5 minutes, not only for 5 minutes, these resistive states could be stored, but for a longer period of time, and even longer. Just these experiments were not long enough in order for these memristors to change the memristive state. So we could say we could be sure that the memristive states did not change in time. And the memristive state, once again, I will highlight that no additional external voltage was needed to store these states. First, we we found the state. So only this first point, for this first point, some voltage was needed. We applied some voltage to come to this state. But then all the other, all the time after that, we didn't need any additional voltages. So the state was preserved in its initial state. Okay, also the endurance of the structures was pretty high. The number of the stable resistive switching cycles was more than 1,000. So this is a good number for the memristors if we compare with the literature numbers. And here we come to an interesting part. If these memristors obey the biologically inspired algorithms, can we change the conductivity of these memristors according to them? And it can be seen here that yes, we can. We used the bi-triangle spikes. We applied presynaptic and postsynaptic spikes of the amplitude of 0.6 volts, and the duration of the spikes was 400 milliseconds. So one of the T-pulse here, it was 200 milliseconds, and all spike was 400 milliseconds. So the pre-spike, the pre and post spikes, they were identical, and they were applied just as you would apply. You would think they come to a synapse. And it can be seen that if a presynaptic spike was the first one, the conductivity of the structure increased. So this kind of connection is a good connection, and its weight should increase, so its conductivity increases. But on the other hand, if a presynaptic spike comes after postsynaptic spike, this kind of connection should be depressed. It should be lowered, and its conductivity is decreased. And it can be seen that this kind of dependence was observed for different states, different initial states. So first we put a memristor in some state as before, as it was shown here. Yeah, we put the memristor in some state, one of 32 states. Yeah, and then we applied the spikes. And this was true for 3 different states. But the amount of increase and decrease of the synapse, it depends on the initial state, of course. So if the initial state is low enough, then the increase of this state is dramatic. If you compare to already high resistive state of 1 millisiemens. So we have observed that the conductivity of our memristors could be changed according to bio-inspired rules. This made us very hopeful for the implementation of these memristors in a neural network. But first of all, we proved that the stochasticity of memristors is not very high. Already this figure, all of the points here are mean points for 10 experiments. So 10 experiments were conducted, and here the mean points are presented. And our goal was to prove that the memristor variability doesn't change the STDP curves very much. It can be seen here that we chose 3 different memristors, completely different, well, the same structure, but they were different structures. The same structure but different top contacts. Yeah, so 3 different memristors, and we can see here that if we put all these memristors in the same initial state, they behave in the same way. So the stochasticity of the structure doesn't influence the STDP characteristics that much. This picture, we can be sure that it will be the same for all of the memristors, nanocomposite parylene memristors. And also the amount of the change, of the weight change, can be changed if we change the amplitude of the spike. So I told that this amplitude of the spike was the same, yeah, but if we change it, we can change also the amount of memristor reaction to the spikes. We can make it lower, we can make it higher. So basically these STDP curves can be managed in a way that we want them to be. Also, another way of changing the resistive state was demonstrated. So this is a more biologically plausible, yeah, biologically inspired, but also a simple potentiation depression curve can be obtained from our memristors. When I say that potentiation depression curves, in order to depress the memristor, we had to apply negative voltages, and it slowly, gradually, the conductivity of the memristor decreased. Here, this is the pulse number of negative amplitude that was needed to depress the memristor from the initial state. So initially it was in a high conductivity state, yeah, and with all the voltage pulses, 50 voltage pulses, it came to this state. And then if we switch the polarities of the voltages and apply positive voltages, the conductivity of the memristor grows. So basically the weight of the memristor could be changed according to the BO-inspired algorithms, and also just by applying some voltages and potentiation depressing the structure. But of course, here also should be some kind of stochasticity, and if we see not only the mean curve, but all the curves that were obtained, you can see that, of course, there is some kind of stochasticity in the memristor. So if we apply, for example, 10 pulses, negative pulses, it is not, we are not 100% sure that the memristor is going to be here. It can be in a lower state, in a higher state, in a small window. The window is not that high, but there can be some stochasticity in the weight weight change. Okay, so I arrive to our main result, the neural network simulation. Here I will stop a little bit more in order to clarify all of the details. So as I have already said, our idea was to have these connections, synapses between neurons as memristors. So we wanted to put memristors in these connections, the memristive characteristics, memristors, anyway. We did not create a hardware neural network, we just simulated it. We simulated how the weights of the neural network could change according to memristic characteristics, according to experimental results. And they could change in two different ways. So the weights of the memristors could change according to biologically inspired algorithm, STDP curves, yes, and the weight could be changed just with potentiating, depressing the structure with the singular voltage pulses. And these are two algorithms with which the weight or conductivity of a memristor could be changed. So we loaded all these rules to the neural network, to the simulated neural network. So in our simulated neural networks, the weights didn't change randomly or didn't change as they wanted according to the backpropagation algorithm, but the weights changed in accordance to the experimental results. So we created two similar networks, one formal neural network with potentiation depression curves, and one spiking neural networks where the weights were changed according to STDP rules. They were all, the neural networks, the structure of the neural networks was identical. So our task was to classify the numbers. The numbers consist of that much pixels. So we have 5 lines, and we had some kind of pre-neural network data pre-processing, yeah, in order to feed these numbers to the neural network. So each line here of this number is represented by an input neuron. So we can see here that there are 5 inputs. So, and here are 5 lines. So each line was first preprocessed and then fed to the input neuron. But also there were 5 additional neurons, input neurons, with inverted data. It was necessary for the spiking neural network, and I will not get into details, but in general, we got 10 input neurons from each picture of the number. Each picture of the number gave us 10 input neurons, and at the output we had also 10 neurons. So from 0 to 9 we wanted to classify the numbers. Okay, so this is our main result to date. The SNS, it's the neural network with this STDP, and FNS with the potentiation depression curves. And it can be seen here that the SNS without variation and with variation, experimental variation, yes, the inherent memristic variation, it shows good results in this classification, but still it loses to the formal neural network with experimental variation. So we can see here that experimentally derived characteristics for potentiation depression curves, they give us a higher accuracy. The neural network, not bio-inspired, yeah, it gives us higher results than the bio-inspired spiking one. But if the variation of a memristor increases, it can be seen here, the green line. If, for example, after time, the variation of the memristor increases, which is a very probable thing to happen, then the accuracy of the data classification decreases, and it is going to decrease even more if the variation increases. Here, the main thing that we see in this graph is that even with higher variability, 61, the CV is the coefficient of variation, the spiking neural network, the VO-inspired one, yes, it has higher coefficient of variance, and it still shows better results than the fairness with the lower variation. Yeah, here is variation 20%, and it already shows lower values, higher standard deviation of these values. And if the coefficient of variation would have been 60, as it is here, then the results for the formal neural network would be even less than for the spiking one. So here we can see that if we change the weights in the neural network according to the STDP biologically plausible algorithm, we get a neural network that is prone, which can be to which we can have some, in which we can have some kind of staticity, but it still demonstrates good accuracy. So this kind of biological algorithm is okay with memristor variations. Memristor variations will always be, this is an inherent characteristics. So we can say that spiking neural networks are kind of medicine for the memristor stochasticity. So to conclude my talk, three main ideas were discussed, that the nanocomposite memristors, they demonstrate better resistive switching characteristics than pristine parylene memristors. Also, we demonstrated that these nanocomposite memristors have characteristics which are suitable for neuromorphic applications, to make a neural network based on these memristors, in a role of the synapse. And also we showed that STDP based neural network demonstrates low stochasticity, even lower stochasticity than the fairness, yes. So it has really a low stochasticity for the classification accuracy of the numbers patterns. So this is the end of my talk. Thank you for your attention. If you have any questions, I guess there will be some discussion part of the talk. Thank you very much for your attention.